Have you ever wondered what your favorite 12,000-pound land mammal and the weird tasting candy in your bathroom have in common? Well, neither have I. But today, these two things will help us learn about an area of chemistry called chemical kinetics. More specifically, they'll help us learn about something called reaction rates and how we can speed them up or slow them down with something we chemists refer to as catalysts. But before we get into that, let us introduce ourselves. I'm your friendly neighborhood no-scoping, 90s building, bus driver, thanking, Victory Royale specialist, molar ratio man. And these are my deadweight, wonderful teammates.
Hiya kids, my name's King MC. I enjoy long walks on my skyblock island, and mining for hours, days, weeks, even months on end, void of any type of human contact or stimulus that isn't the sound of my pick hitting against the hard stone as I venture into the cold dark abyss that is my—
I may recently just learned my ABCs, but don't come out just yet, because when it comes to math, I have no equal. So remember to use creator code I love calculus on your next Robux purchase.
Okay, now that we got all the formalities out of the way, let's make like the battle bus and get straight into it. Right. So first, let's start with trying to understand what area of chemistry we're going to be talking about today. Chemical kinetics. While these words may sound scary and complicated at first, don't worry about it, because they are. But luckily for you, because you guys still have hopes and dreams from never actually having taken an AP class before, today we're just going to focus on trying to get a basic understanding of what these things are. So when we talk about chemical kinetics, we're talking about chemical reactions and their reaction rates.
In simpleton terms, a chemical reaction is a process where you get two or more things and combine them, or if you're using scientific terms, squish together to get a totally different thing. Chemists call the things you squish together reactants, and the new thing you make, or rather, produce, the products. While the rate of a reaction is how long it takes to make the new thing. Think of it as the speed of the reaction. Here's an example. Let's say you're playing Minecraft. You just came back from the nether and you want to make a potion for the first time. So you go into your brewing table, you grab some netherwort and some spider eyes. These will serve as your reactants. Then from combining the reactants and water, you create a product, which in this case is a potion of poison. Not too bad. And as for the reaction rate, think of it like this. Think of a reaction as a road trip. You're traveling from point A to point B. Point A being our reactants and point B being the product. And you're traveling between the two by car. The car, this is the focus of our analogy because in this case, the car would be our reaction rate. Think about it. The amount of time it takes us to travel from point A to point B is directly linked to our car, specifically how fast our car is going. This idea is helpful because it explains why not all experiments take the same amount of time. Not all cars are made of the same things, so it would make sense that some cars go faster than others. Some are heavier, some are made of lighter things. If you had to take two chemical reactions, such as rust building up on metal tools and an explosion, you could equate rust reaction rate to a toy tricycle, and an explosion to Lightning McQueen traveling 9,000 miles per hour in the Piston Cup Finals. Ka-chow!
Today, our reaction will be the decomposition of hydrogen peroxide, also known as H2O2. Up until now, we talked about the reactions that involve combining two things together, but in a decomposition reaction, you do the complete opposite. Instead, you take the two things that are squished together, that make up one thing such as hydrogen peroxide, and rip them apart into separate things, which in this case would be water and oxygen gas. A good way to wrap your head around it would be like this. Think of H2O2, hydrogen peroxide, as a big bag of trail mix. Altogether, the ingredients make trail mix, but if you were to separate all the ingredients in the trail mix, you'd be left with piles of peanuts, pretzels, seeds, fruit, and some yummy M&Ms. While altogether, these things make up trail mix, on their own, they're an entirely different snack. Now for the main event, catalyst. And no, when I say catalyst, I'm not referring to the heavily influential feline mumble rapper Catalyst. All males aside, a catalyst is a substance that helps a reaction reach
maximum overdrive.
Reactions need certain amounts of energy to proceed. Catalysts are totally awesome sauce because they help us out by lowering the amount of energy we need to have a reaction. Going back to our road trip example, each reaction, or in our case, each road trip, has a specific amount of gas that is required in order to be able to drive the entire distance. You need enough gas to be able to drive through all the twists and turns you'll encounter on your drive. But there's a way to decrease the amount of twists and turns you have to do, with the help of a handy-dandy global positioning system, or GPS for short. If you ever use a GPS, you know that a GPS shows you the shortest, most efficient route to your destination. So, because a GPS lets you take a shorter, more efficient route, you don't have to drive as long as it would normally take you. And because you need to spend less time driving to your destination, you don't need as much gas. Think of a catalyst as our GPS, except instead of lowering the amount of gas you need for your car, an actual catalyst lowers the amount of energy required to complete the reaction and create products.
Quite stale, wouldn't you think? It looks like nothing's happening at all. And while it may look like that at first, I can assure you that something is indeed happening. This particular reaction can seem invisible to the naked eye, but on a molecular level, hydrogen peroxide is decomposing into water molecules that stay in the container and oxygen gas that leaks out into the open air. And if you're to leave this hydrogen peroxide alone for long enough time and come back to it later, all the hydrogen peroxide in the container would have decomposed and all you would have left in the container would be water. Cool, right? Well, it may not be as cool as what we're about to show you, but it's because of this seemingly dull and boring reaction that we're able to do what we're about to do right now. Now for the main event. Now we're going to try the very same reaction, but with a catalyst this time. In the blue corner, weighing in at 7 tons and standing at a little under 4 meters tall, the two-tusked titan, Lexa Danta! And the challenger, coming in the red corner, weighing in at a whopping 100 grams and descending from aisle 4 of your local Target, the perfectly priced puncher to ever play, Paw Patrol Toothpaste!
Now, as I'm sure you've all figured out by now, today we will be making elephant toothpaste. And in order to do that, we will be using the decomposition of hydrogen peroxide that was just shown and a catalyst. For our experiment, we've made sure to prepare all the ingredients. Before adding in the yeast, we add dish soap and food coloring to make the mixture a bit extra, for some style points if you may. These things don't react or add anything to the reaction itself. In reality, the soap just helps trap the oxygen gas that's being produced, which makes more bubbles and just overall better foam quality, which holds up pretty well, while the food coloring is just there so it looks cool. Now, remember that this is the same exact reaction that we showed you before, except now we have a catalyst that has increased the reaction rate. By increasing the reaction rate, instead of having all the hydrogen peroxide decompose slowly bit by bit over a long period of time, just like in the first case, because of the catalyst we added, the decomposition rate of the hydrogen peroxide has been drastically increased, so all the oxygen gas comes rushing out all at once.
Wow, molar ratio, man. This chemical kinetics thingy sure is interesting.
It sure is, isn't it? Well, that's about all the time we have today, so let's wrap things up.
Today, we learned about how hydrogen peroxide is constantly breaking apart into water and oxygen gas in a decomposition reaction. We also learned how all reactions have something called a reaction rate that determines how fast the reaction will happen. Finally, we learned how a catalyst can make a super slow reaction and make it go super fast. Ka-chow! We then used our newfound knowledge to take the slow reaction of hydrogen peroxide and make it zoom by using catalysts. And then we finally were able to make elephant toothpaste.